Our last example, we want to determine algebraically whether the functions in each pair are inverses or not. So there's two ways that you can go about this. The first way would be start with one, switch x and y, and see if you get the other one. If you do, they're inverses. If you switch x and y and the equations don't match up, they're not inverses. So for A part I have this. I'm going to switch x and y, so I get x equals 3y minus 6. And I'm going to solve for y, so I'm going to move the 6 over, divide both sides by 3. Do they match up? No. The second way you can check if something is an inverse is similar. You know how, well, for those of you that watch the videos and for those of you that were here, remember how I had like the two machines beside each other? If they're inverses, you put in, like we had a number, we put in a number here, say out pops a 5, all right? Then if this is an inverse and I put it into the other one, the same number would pop out again. Does that make sense? I picked a really easy one. What was my formula here? X plus 3. What did I do to my answer? X minus 3. Those are inverses of each other. Okay? If something is an inverse, it means that if you put in x, you should get x when you come out. So what happens when I put in x in here? Out would come x plus 3. What happens when I put in x plus 3 into x minus 3? I would get x plus 3 minus 3, right? Because you plug in the x plus 3 for the x. And, oh, my 3's go away, I get x. If this happens, it is an inverse. Look what happens in ours. Now, notation-wise, if this is f of x and this is g of x, what we're doing when we do both in a row, we write it like this. G of f of x. You did f of x first, got an answer. Whatever answer you got, right, got thrown into g of x, and we see what the answer is. So in our example here, I'm going to call this first one f of x and the second one g of x, and I'm going to test if I get x by plugging things in. So first of all, I'm going to plug x into f of x. And I have to plug 3x minus 6 into the second one. The second one's equation was x minus 6 divided by 3. And if I plug in 3x minus 6 in for the x, and I simplify this, I would get 3x minus 12, which is equal to x minus 4. It does not equal x, and it is not an inverse. I think you like method 1 better, where you switch x and y and see if they match up. In calculus, we use method 2 a little bit more. Okay, so I'm just showing it here now. It's a nice way of quickly checking things if they're an inverse in calculus. where you plug one function into the other function and see if you get x. In this one we didn't, so it's not an inverse. Scroll up, split the page here. Okay. 2. Couple things to notice in 2. First of all, I'm going to highlight that part. They have a comma and then they have x is greater than 0. That is a domain restriction. Can you see that negative x squared plus 3 is a parabola? And having that domain restriction, they're only taking half of it. Is the half that they picked this square root, or is the half that they picked the negative square root? We have to find out. So, how do you find an inverse? Pick one of them. I'm going to pick the top one, and I'm going to switch my x and my y. Okay, I'm going to move the y squared to this side. I'm going to move my x to this side. And I'm going to square root. And when I square root, I get the plus or minus. Our question is it the plus or is it the minus? Okay. One way you could do it is you could look at the graph. If we looked at the graph, negative x squared plus 3, parabola flipped down, shifted up 3 units. The parabola would go on both sides, but we only have, when x is bigger than 0, we only have this half. Okay? So when you would switch, oops. Instead of 0, 3, I would have 3, 0. Instead of 1, comma 2, I would have 2, comma 1. Does the blue graph have a vertical reflection? No. So you could tell from graphically that it's the positive one. Another way that you could find out graphically that it's the positive one is you could actually take the domain restriction, and when you switch x and y, that makes a range restriction. And if the y values have to be bigger than 0, you would know right away it has to be the positive one rather than the negative one. So lots of little details in this question, right? It's not just about switching x and y and finding it out, but we also have to be analyzing which part are we using and does it match up with the graph. So we already drew both graphs here in the blue graph. So we've done part B for that one. We've verified it graphically. If you had to graph, and we're going to skip this right now because you could graph y equals 3x minus 6. It has a y-intercept of minus 6 and a slope of 3. And if I was graphing this 1, I would change that dividing by 3 to 1/3 x. And 6 divided by 3 is going to be 2. So 1/3 x minus 2, and then you know that one has a y-intercept of minus 2 and a slope of 1/3. And if you draw both of those graphs, you'll notice they're not a reflection over y equals x. A point on, like, this first graph has the point 0, minus 6. The second graph does not have minus 6, comma 0. All of your x's and y's would have to switch for an inverse. And it doesn't work for that second one. Okay, I'm going to get you to circle 7, 8. 11 and 13, and I put in my notes that 11 and 13 are problem-solving questions, so they make you think a little bit.